Hi everybody, this is lecture 7 about rotational motion. So all motion we've discussed up till now has been linear motion, which is in a straight line. So this is going to be rotational motion, this lecture. And all the definitions we've talked about before, like inertia, displacement, velocity, acceleration, force, energy, momentum, are all the same. We're just going to put the word rotational in front of it, but all the ideas are the same. And Newton's laws are going to be the same as well. So we're going to talk about rotational Newton's laws as well. Okay, so motion, it's motion. What is circular motion? It's motion around a circle or a curve. The same laws of physics apply. The same definitions can be used. So we'll add the word angular or rotation, rotational to a lot of words like inertia, rotational inertia, angular displacement, rotational velocity, rotational acceleration. All of these will be the same. And we can redefine Newton's laws for circular motion. So if we understand our laws from linear motion, regular Newton's laws, they transfer over. Okay. So rotational form of Newton's laws. First law, an object or system of objects will remain in its rotational velocity unless acted upon by an unbalanced rotational force. And we'll learn later that rotational force is called a torque. Okay. And can you come up with rotational form of Newton's second and third laws? Well, Newton's second law is force equals mass times acceleration. So that would be torque, or rotational force, equals rotational inertia times rotational acceleration. And the third law would be for every torque, there's an equal and opposite torque. And remember, those are on two objects. Okay, a net unbalanced rotational force will cause the object to have a rotational acceleration. So that's similar to Newton's law, second law. When two objects exert rotational forces on each other, these rotational forces are equal in magnitude in opposite directions. So that's Newton's third law for rotation. Okay, so for circular motion, there's this idea of tangential speed, which is the distance traveled by a point on... Okay, let me read that again. The distance traveled by a point on the rotating object divided by the time taken to travel that distance is called the tangential speed. So if you're sitting on a circular object going in a circular motion, then your actual speed is your tangential speed. Your rotational speed is how quickly you're rotating in RPMs. So points closer to the circumference have higher tangential speed. That points closer to the circumference, that's towards the outside, have a higher tangential speed than points closer to the center. So this bug will be moving at a certain speed, and this bug will be moving twice as fast if this record is rotating. Okay, so more about rotational speed. So that was tangential velocity, which is how fast you're moving around. And rotational speed is how quickly you're spinning. So that's in RPMs, rotations per minute, or revolutions per minute. Okay, all parts of a rigid merry-go-round or turntable turn about the axis of rotation in the same amount of time. So all parts have the same rotational speed, even though different parts have this different tangential speed. So all parts have the same rotational speed. Okay, circular motion, speed. A and B have the same rotational speed, but B has a greater tangential linear speed. So if this thing is rotating, this circle, A is moving slower than B because it's on the outside. But they both are moving at the same RPMs. So tangential speed is equal to radial distance times rotational speed. So B has a higher tangential speed because it has a higher radial distance, even though the rotational speed is the same as A. Okay, acceleration. A and B have the same rotational acceleration, but B has a greater tangential linear acceleration. So same thing applies. So B has a greater tangential acceleration because it has a greater radial distance, its distance from the center, but the same rotational acceleration. Okay, tangential speed versus rotational speed. So if these are two gears or circular things connected by a belt or a chain, then both of the outside here of this one and the outside here of this one will be moving at the same tangential speed. So the rotational speeds will be different, but the outside of the circles will have the same tangential speed. So that's what a chain or a belt does, is to make sure the outside of the two circles or gears or whatever they are have the same tangential speed. So is the rotational speed of the two flywheels the same? No. The smaller one rotates faster. Is the tangential speed the same? Yes. The belt chain connecting the two is moving as a solid object, so it's not stretching. So the tangential speed on the outside of the smaller flywheel is the same as the outside of the larger flywheel. Okay, so let's talk about tangential speed and rotational speed of a rigid object. So this is a merry-go-round. There's the horses on the merry-go-round. Is rotational speed for all of the horses the same? The answer is yes. If it's solid, it's going around at the same rotational speed. All the horses move at the same rotational speed. Is the tangential speed the same? No, because they're at different distances from the outside. So the inner horses will be moving more slowly than the outer horses. Okay, let's check ourselves. A ladybug sits halfway between the rotational axis and the outer edge of a turntable. When the turntable has a rotational speed of 220 RPM and the bug has a tangential speed of 2 centimeters per second, what will the rotational and tangential speeds be of her friend who sits at the outer edge? So since the first ladybug is halfway and the second ladybug is sitting at the outer edge, the first one's moving at 2 centimeters per second. We know from this one, double the radial distance, double the tangential speed. So that means it would be 4 because the initial one was 2. Okay. All right, let's talk about forces. So a centripetal force is any force directed toward a fixed center is called a centripetal force. So this girl who's rotating this cup around above her head, the force on the cup, keeping it in a circle, is in towards the center, in toward her hand. We call that center-focused force, centripetal force. Okay, yeah, center seeking towards the center. Okay, centripetal force, let's keep going. Its direction is towards the center of the circle of rotation. So if you've ever been on one of those carnival rides where it spins you up and you stick to the walls, the force on each one of these people is in towards the center of the circle. That's a centripetal force holding those people in circular motion. So the centripetal force is not a separate force, but rather it's a combination of all the forces, ensuring that something goes in rotational motion, or circular motion in this case. And here's the formula for centripetal acceleration, which is acceleration is v squared over r. So the center of the circle for these people is the radius of the circle. And their tangential speed is v, and the radius, we could measure it, of the circle is r. Their acceleration they would feel being pushed in towards the center as they go around would be v squared over r. We'll do a problem. Okay, if we're in a car rounding a bend, then the centripetal force is in towards the center of the bend. That stops us from skidding on the road. So we feel like we're getting flung to the outside of the car, but that's not what's actually happening. Is a force is directed in towards the center of rotation of the curve to keep us in the curve. So if a road is wet or going too fast, we will go straight off the road, off to the outside, because the force keeping us in the curve is insufficient. Okay, let's do a question. Suppose you double the speed at which you round a bend in the curve. By what factor must the centripetal force change to prevent you from skidding? Okay, so to look at that, we'll look at this formula here, or actually this one. The force is equal to mv squared over r. Since we're doubling our speed, we're quadrupling the force. It's going to be 4 times. And yeah, that's because centripetal force is mv squared over r. So we double the speed, double the force. Suppose you take a sharper turn than before and halve the radius. By what factor will the centripetal force need to change to prevent the skidding? Okay, so look at the old formula here. We have, down here, we have this. So it's not squared, it's just to the first power. So if we have this, it doubles this. So that means the force will be double. Okay, same formula. Okay, although centripetal force is center directed, an occupant inside a rotating system seems to experience an outward force. This apparent outward force is called centrifugal force. Centrifugal means center fleeing or away from the center. So this is a fake force. We call it a fictitious force that we feel when we're in the car, flinging us to the outside, but it's not real. The actual force keeping us in the car is towards the center of a circle or center of the bend. Okay, So let's say this is the girl again with the cup rotating above her head, going around in this circle. And the string is got a force directed towards the center of the circle, holding the cup in place. So as the, let's say, I've got something on my desk here, I got a cup. This cup goes around in a circle. The force is always directed towards the center of the circle so that it stays in circular motion. If the string is cut in the cup example here, then the force causing circular motion, the centripetal force, will be lost, and the inertia will take the cup in a straight line tangent to the circle. Okay, so that outward force we think we're feeling is actually not real. It's actually we want to go straight, and forces are making us go in a curve. So when the force is cut, we go straight. We don't go away from the circle, we go straight. Okay, so centripetal force versus centrifugal force. So centrifugal force is not real. It's the feeling of us when we round a bend, of us going out away from the center of the bend. But the force that's directed in towards the center of our circle or our bend is what's keeping us or an object in circular motion. So let's just read this. What happens if I swing a can in a circular path? I need a centripetal force to keep it in a circular path. That's the string force. And the cup will feel a centrifugal force, feeling like it's getting flung out, but it's not real. The bug feels pressed against the bottom of the can. Oh, so we got a bug in the can here. The bug feels pressed against the bottom of the can. It feels like there is a force pushing it away from the center of the circle. That's the centrifugal force. So the bug is actually getting supported by the base of the can inward towards the center of the circle, but it feels like it's getting forced outward. And that's the fake force, the centrifugal force. If the string suddenly breaks, the can flies off in a straight path tangent to the circular path, and the bug will move in a straight line tangent to the circle. If centrifugal force existed, the can would fly off in the radial direction, not tangent. So that would mean instead, when the string is cut, the can would fly outward, but instead it flies straight. So what makes the object move around in the circle? It's the centripetal force. In this case, it's the tension in the string. So the centripetal force always points to the center of the circle and is always perpendicular to the direction of velocity. So at this particular point, velocity is tangent. Force is directly in towards the center of the circle. At a different point, velocity is tangent. Force is in towards the center of the circle. And these are centripetal force and centripetal acceleration to keep the object in circular motion. Okay, so in space, and in other situations, you can simulate gravity with rotation, because this bug that was in the can feels as if it's in a gravitational field when it's on the edge of a rotating, in this case, can. So a space station, if we could rotate a space station, then people could sit on the outside of the space station, we could spin it up, and that would give us artificial gravity. So if this space station right here is rotating, and this person is sitting on the outside wall, he can feel as if he's in a gravitational field. So this is simulated gravity. Sometimes you'll see this in movies and TV shows to give simulated gravity. Okay, center of mass. Center of mass is where if we averaged out the positions of all of the masses in an object, we could act as if it's concentrated in the center. So let's read this. Most of the time, when thrown in the air, an object will rotate around its center of mass. Okay, so this baseball bat here thrown will be doing some complicated rotation, but the center of mass will follow a nice path, and the bat will rotate around that point. The center mass is the average position of all the masses all the mass that makes up the object. For a symmetrical object such as a ball, the center mass is directly at the center. For an irregularly shaped body, the center of mass is closer to the heavier end. If all the mass was concentrated in one point, that would be the point of rotation. So for complicated things like animals and horses and people, the center of mass, we can change where the center of mass is based on our body orientation. And it's a complicated system. So where the center of mass is at any point in time is difficult to answer. Okay. Center of gravity is a similar idea, but this is the average. If gravity acts on the entire object, where does the average gravity force act. So let's read this. Center of gravity is the average position of the weight distribution. Since weight and mass are proportional, the center of gravity and the center of mass usually refer to the same point of an object. So it's not always the same, but for almost all purposes, center of gravity, which is the average of all the forces of gravity on the object, is the same place as the center of mass, which is the average of all the masses in an object. So to determine the center of gravity, suspend it from a point and draw a vertical line from the suspension point. Okay, so we're not doing experimental physics here. So that's how we would do it. We don't need to worry about that. Okay, center of gravity stability. So if something is going to topple, then the center of gravity will be outside of its support. So if I have this cup here, supporting it, if the center of gravity moves outside of the support, I know it's going to topple. If the center of gravity stays inside the support zone, it's not going to topple. So here's this person making L shapes. So this L shape, the center of mass is, okay, hold on, let's go with the person first. Here, the center of mass is somewhere in the middle here, over her feet. But here, the center of mass is no longer over her feet. So in this case, she'll topple. In this case, she will not topple. This object here, if it's situated like this, the center of mass is over the support, not going to topple. But if we flip it upside down, this is the support, center of mass is outside that, it's going to topple. I think we have some intuition about how things are going to topple. And when things look like they're going to topple, the center of gravity is outside of the support structure. Okay, rotational inertia. So this is how difficult it is to rotate something. And if you remember, for regular inertia, it was its resistance to change in motion. So things with high inertia are difficult to accelerate, and things that are low inertia are easy to accelerate. Same thing with rotation. Things that are easy to rotate have low inertia, and things that are hard to rotate have high inertia. So this is a combination of mass and distance from the rotation point. So in this case, this weight here with the masses close to the center of rotation is easy to rotate. If the masses are far away, difficult to rotate. Let's read this. An object rotating about an axis tends to remain rotating about the same axis at the same time, at the same rotational speed, unless interfered with by some external influence. Okay, so that's a reiteration of inertia. We're going to move at the same rotational speed forever, unless there's an external torque that comes in and causes changes. The property of an object to resist changes in its rotational state of motion is called rotational inertia. So it depends on the mass of the object and the distribution of mass. We talked about that. Okay, so for tightrope walker, they use this big long stick. What they're doing is they're taking a small mass, but they're moving it away from the center of rotation, so they can get a lot of rotational inertia. So any micro movements they have won't translate into big changes in rotation because they've got a high rotational inertia with the big stick. Now if we take a pencil, if we try to, let's get a pencil here. If we go edge on, rotating this way is easy. If we try to rotate like this, that's difficult. This way, all the mass is around the center of rotation right here, very small. But here, I try to rotate like this, very difficult. Well, it's not difficult because it's pencil, but it's more difficult than this way. And the hardest is if I went from one of the edges. Try to rotate like that. I can't quite do it with my hand. Okay, and that's all about the mass of the pencil and where the mass is relative to the center of rotation. Okay, so more rotational inertia depends on the mass, distribution of mass relative to the axis of acceleration. We talked about that, and depends on the location of the axis of rotation. And the rotational inertia is proportional. This is what this alpha looking thing here, it means I, rotational inertia is proportional to mass times radius squared. Okay, let's look at some objects here. So a simple pendulum that's going in a circle, or it's maybe going back and forth. That's mr squared. So the mass of the object times the radius of the string. For a hoop, it's mr squared. For a hoop about a diameter, okay, so it's rotating around this point up here. It's going all the way around in these big loops. It's 1/2 mr squared. a stick around the end, 1/3 mr squared. So this stick is going around like this. Stick around the center, 1/12 ml squared. So this thing is going round and round. Solid cylinder. I have a solid cylinder. I do not. 1/2 mr squared. And a solid sphere rotating like the Earth or a billiard ball or something is 2/5 mr squared. So we've got all these different formulas for all these different shapes. Okay, so a hoop and a disc are released from the top of an incline at the same time. Which one will reach the bottom first? Well, the disc is going to have an easier time rotating because of its shape. And the hoop is going to have a more difficult time rotating because all the mass is far away from the rotation center. So that means the disc is going to get there first. Okay, and we get that from either knowing that the mass farther away is higher inertia, or we can look at these formulas. A cylinder is 1/2 mr squared versus mr squared. Okay, angular momentum. So before, momentum is P equals mv, and that was momentum equals inertia times speed. Here, it's going to be the same thing. Angular momentum is equal to rotational or angular inertia times angular velocity. I guess it's the same idea. So this is analogous to linear momentum was mass times velocity. Okay, so we've got a lot of examples like ball going around in a circle, Earth going around the sun. This pencil, if I rotate it, it's got angular momentum because it's rotating. Anything that's rotating, tires on a car, steering wheel on a bus, Ferris wheel, all of these things have angular momentum. Okay, suppose you are swirling a can around and suddenly decide to pull the rope in halfway. By what factor would the speed of the can change? Okay, so we're reducing the radius by 2. So if we look at this, we're going to reduce the angular inertia by reducing the radius. We have some formulas here. This is the formula. We're going to reduce the radius by 2, which means we're going to reduce the inertia by 4. Okay, so if we go back here, we've reduced the inertia by 4. So that means we're going to reduce angular velocity by, increase angular velocity by 4. Now, angular velocity is, let's get back to, where are we? I'm going to go all the way back up here. We've got a formula. Here it is. Angular velocity goes up by 4. Radius went down by 2. So together, that means the tangential speed goes up by 2. That's 4 for angular speed, 2 for radius. So total is a change of 2 in speed. Let's go make sure that's right. Almost there, almost there. There we go, double. Okay. Conservation of angular momentum. So we talked about this. It's the same as linear momentum, but we restate it with the words angular in there. So if there's no external net rotational force or torque acts on a rotating system, the angular momentum of that system remains constant. So before, it was no net force on an object, means linear momentum stays the same. Here, it's no net torque on a rotating system, means angular momentum stays the same. Okay, so it's restated here. So when this person on this turntable pulls the weights in, their rotational speed goes way up and they get dizzy. Okay, let's do a problem. Suppose by pulling the weights inward, the rotational inertia of the man reduces to half its value. By what factor should his angular velocity change? Well, let's look at the formula. We're going to reduce this by half, which means we're going to double that, because we know this is the same before and after. There we go. Double. Okay. And here we have this equation down here. So angular inertia times angular speed equals angular inertia times angular speed. This big I and the small speed means small I and big speed. That's what's happening here. Okay, torque. This is a rotational force. Torque depends on 3 factors: magnitude of the force, the direction in which it acts, and the point at which it's applied on the object. So the equation is torque times the lever arm times the force. Okay, so let's do some pictures here so we can see this. So torque, which is this Greek letter tau, is equal to where the force is applied, the radius from the center of rotation times the force. Okay, so the reason we use wrenches is to get more torque for the same force. If we tried to grab a screw with our hands, we couldn't exert enough force on it with our hands, but we get a torque. That gives us mechanical advantage, and we can exert a lot of force on the screw, a lot of torque in this case, to rotate the screw out of its position. So that's why we use things like torques, like wrenches and levers, so we can get torque advantage. Okay, and this is explaining that. So let's see the first picture. This pulling at this angle with the, I think we do this when we if you actually want to unscrew something or screw something in, your arm sort of automatically gets into the high torque position. So if you've got a wrench and we want to rotate this bolt here, pulling at an angle isn't going to do it. Pulling at 90 degrees is the best way to do it. Okay, and then if you get even a longer wrench, that's even more torque. Okay, that's by this. So the longer that is, the more torque you have. Okay, so I suggest you try this. Get a wrench, get a bolt, and play around, see if you can get a feel for what torque feels like. Okay, and this is a seesaw balance. And if these people are in equilibrium, we talked about that, then their forces are all equal to 0, and their torques are all equal to 0. That's called equilibrium. So forces all added up equal to 0, or all the torques added up equal to 0. Okay, which in this case, if everything's nice and 90 degrees, we get all RF1 equals R1 F1 equals R2 F2, which in this case, I think this is like, say, Kate and Alice. So R of Kate away from the fulcrum times her force, her weight, and then the radius of Alice away from the fulcrum times her force or weight. Those are going to be in balance if this seesaw is not moving. Okay, let's do this problem. I think this problem is not correct. I don't think they give us enough information. Let's go through it and see if we can understand it. Suppose the girl on the left is suddenly handed a bag of apples weighing 50 newtons. So she's handed a bag of 50 newtons. Where should she sit in order to balance, assuming the boy does not move? So if they're in balance here before she gets handed the apples, then she's going to need to move inward so that her R is reduced for the higher force, so that her torque is the same as it was before, so this stays in equilibrium. But they don't give us her original mass. So we know it's going to be less than 3, but we don't know what the value is going to be. And then I see this explanation here, and it doesn't make sense to me, because the original torque is 3 meters times 250. That must be her original weight. That's 750 Newton meters. And the new torque is going to be the new lever arm times the new force. And then they plug in the force and the torque, and they get the new lever arm to be 2.5. But this is wrong, because the new force is the same as the old force. So if we divide this through, we would get 3 again. So they don't give us enough information to answer this question. And this answer is arrived at by incorrect math. Okay, but we could figure this out if we knew her body mass, meaning we knew her weight, because we could multiply it by g. Okay, let's continue. Torque statements of Newton's laws. An object or system of objects will maintain its angular momentum unless acted on by an external net torque. Okay, that's very similar to an object or system of objects will maintain its momentum unless acted on by an external force. Okay, a net unbalanced torque will cause the object to have angular acceleration. Yep, so torques cause angular accelerations, and forces cause linear accelerations. When two objects exert torques on each other, the torques are equal in magnitude and opposite direction. That's Newton's third law. Okay, let's do some questions, more questions. To impress his friends while riding on a carnival Ferris wheel, prankster Paul gets out of his chair and climbs along the spoke of the wheel toward its center, while the wheel continues in uniform motion. While climbing toward the center, Paul's linear speed, increases while his angular speed remains unchanged. That sounds good. Decreases. Oh, it's not going to increase because he's moving towards the inside, so it's going to decrease. I said that wrong. So it's going to decrease while his angular speed remains unchanged. That sounds right. And his angular speed won't change because the carnival ride, the Ferris wheel, is probably going to stay at a constant angular speed because of the motors. So his speed is going to decrease while his linear speed will decrease while his angular speed remains unchanged. Okay, and this is really dangerous. Don't do that. When you roll a tapered cup across a table, the path of the cup curves because the wider end rolls, well, it's going to roll faster because the tangential speed of the outside is going to be higher than the inside, and so it's going to go in a curved path. Okay. The rotational inertia of an object is greater when most of the mass is located. Well, we know that's far away from the center. If it's close, it's going to rotate really fast. If it's far away, it's going to be rotating more slowly. So near the center, no. Away from the rotational axis, that sounds good. On the rotational axis, that's going to be almost nothing. Off center, not sure what that means. I think this one is the best answer. Okay. For round objects rolling down an incline, the fastest objects are generally those with the, well, we know the greater the rotational inertia, the slower it's going to get started up. So we want things with low angular inertia. Greatest rotational inertia, no, we don't want that. Lowest rotational inertia compared with the mass, that sounds good. Most streamlining, well, that would help, but we're talking about rotation here. Highest center of gravity, that's not as relevant, so it's going to be lowest rotational inertia. Which of these will roll down an incline fastest? A disc, a hoop, a solid ball, the one with the greatest mass will roll fastest. Well, we got to look at the formulas here. Well, it's actually unknown if we don't know the masses, because if the masses are different and the sizes are different and the radii are different, we don't know. But assuming they're all the same mass and all the same size, then the one that's going to go down the fastest is probably going to be the solid ball. But let's check our formulas here. We're going to go all the way up. That's too far. These formulas. So if they have the same mass and same radius, then the hoop is mr squared. The solid cylinder is 1/2 mr squared. And the sphere is 2/5 mr squared. 2/5 is less than 1/2, which is less than 1. So this will be going the fastest because it's got the least amount of inertia. Let's get to, we go here. So I'm going to go with solid ball. Okay. A torque is a force, like any other force? No. Multiplied by a lever arm, that sounds good. That is fictitious? No, they're real. Accelerates things? No, it angularly accelerates things. So multiplied by a lever arm. Okay. When two children of different weights balance on a seesaw, they each produce equal torques. That's true, because they're in balance. They have equal torques. Unequal torque, that's false. Equal magnitude torques in opposite directions. That sounds good. Equal forces. That's not right. Oh, I see. So equal torques would mean in the same direction. They actually need to be in opposite directions. So the best answer is 3. Equal magnitude, opposite directions. Okay. The center of mass of a donut is located, that's in the hole. In material making a donut, no. Near the center of gravity. That's true, but actually in this case it'll be at the center of gravity over a point of support. Now it's in the hole. Okay. The center of gravity of an object lies inside the object, not necessarily. Lies outside the object, not necessarily. May or may not lie inside the object, that's true. Is near the center of mass. Also true, but it's almost always equal to the center of mass. So the third one is the best answer. An object resting on a surface will topple over if its center of gravity lies outside the object. That sounds good. Extends beyond the support base. Well, center of gravity is a point. There's no extension. Is displaced from its center of mass? Not necessarily. If they're different locations, as long as the support is underneath them, they're good. Lowers at the point of tipping. I don't know what that means. So it lies outside the object. Oh. What did I say? Extends beyond the support base. That's what I meant to say. Because it could lie outside the object. What did I say at the beginning? It has to be outside the support base. Okay. The center of gravity of your best friend is located near the belly button. That's true. At different places, depending on body orientation, that's even better. Near the center of mass. That's true. Almost always the same. at a fulcrum when rotation occurs. I'm not sure what that means, so I'm going to go with the second one. Looks good. When a stable object is made to topple over, its center of gravity is first raised, at first lowered, plays a minor role, plays no role. I'm not sure what this means. I'm going to go with that first raised, because if I want to topple this, I got to bring it up and then down. Okay. First raised. Which more accurately describes what happens in the circular spin cycle of a washing machine. Water is forced away from the clothes. Well, that's sort of true. Clothes are forced into a circular path while water is not. That sounds even better. Because the clothes are kept in a circle, whereas the water can go in a straight line away from the clothes. Centripetal force acts on the water, but not the clothes. Well, that's not true. Centrifugal force acts on the clothes, but not the water. Well, that's fictitious. That's not part of our explanation. I think the second one is the best answer. When you whirl a tin can in a horizontal circle overhead, the force that holds the can in the circular path acts in a direction. It's going to be inward, not outward. Not either inward. Oh, wait. So this, hold on. Let's read this. Be careful. The force that holds the can in the circular path acts in the direction. Okay. So the force that holds the can in the circular path is in towards the center of the circle, not outward, not either or, and not parallel to the force of gravity. It's definitely inward towards the circle. Okay. So let's look at this question. When you whirl a tin can in a horizontal circle overhead, the force that the can exerts on the string acts in which direction? Okay, so this is now the can on the string. We know that's equal and opposite to the other force we just did, which was inward, so this one's got to be outward. A bug inside a can whirled in a circle feels the force of the can on its feet. This force acts in a direction towards the center of the circular path. That sounds right. Away from the center of the circular path, that's the centrifugal force. That's not the can on its feet. Either toward or away from the center of the circular path. It's not either or. It's definitely in single direction. Parallel to the force of gravity, that's irrelevant. It's going to be towards the center of the circular path. Okay, that's the centripetal force. Gravity can be simulated for astronauts in outer space if their habitat is very close to Earth. Well, that's not a simulation. Is in free fall. That's no gravity. That's microgravity, so that everything floats. Rotates, that sounds right. Revolves about the Earth, that doesn't sound right. So if you rotate the spaceship, or the habitat in this case that the astronauts are in, you can simulate gravity. Okay, for an object traveling in circular path, its angular momentum doubles when its linear speed doubles and radius remains the same. Okay, so let's look up how this relates to linear speed. If we go up to, we're talking about angular momentum. We're talking about speed doubling. So we're going to go all the way up to the formulas. Where are we here? Okay, so L is equal to I omega. And what's omega? Omega is angular speed. And angular speed, I'm going to go all the way up to the top here. There it is. So if we double this, and this remains the same, then this is doubled. Then we go back to our momentum formula. If this is doubled and this is the same, then this is doubled. So that's doubled. Okay, so back to the question. Where are we? Don't want to go too far. Okay, so we said for the first one it doubles. So radius doubles and its linear speed remains the same. So linear speed remains the same means the angular speed remains the same. So let's look at, well, that's not exactly true. So what it was, we got radius doubles, linear speed remains the same. So radius doubles, linear speed remains the same. Okay, so if we go to the top here, we got to figure out what happens if radius doubles. What happens to angular speed? So the speed remains the same. So this is the same. So this doubles. So this is half of what it was before. So this is the same as it was before. This is half. Or this is double. So this is half. So omega is half. Okay. And then now I, radius is doubled So this goes up by 4. So I goes up by 4. I goes up by 4. This is halved. So overall, angular momentum goes up by 2. So it's doubled as well. Okay. So I think we're going to have to do this for the last one as well. Let's see here. I don't want to go too far. Okay, so for the second one, also doubles. Okay, so mass doubles, last one, linear speed and radius remain the same. Okay, so that one's a lot easier. If everything else is the same but mass doubles, then we want to look at this. It's I times speed. We know this is the same as it was before, but I is affected. So if M is doubled, R is unaffected, then I is doubled. Since I is doubled and this stays the same, then L is doubled. So all of these, let's go right. Where are we? Here. So all of these are double, so it's all of them. Okay. The angular momentum of a system is conserved. Never. That sounds wrong. Under some conditions, that sounds good. Under all conditions, that's not true. If there's external torques, then it's not conserved. When angular velocity remains unchanged, that's not quite right. Because it's not velocity that's ever. Velocity is unchanged. We can change other things to change angular momentum. I think it's under some conditions. Those conditions are about external torques. Okay. As Earth's daily rotation increases due to tidal friction, the moon undergoes, well, if it's the Earth-Moon system and Earth's rotation rate's going down, that must mean the moon's rotation rate must increase so that to compensate, so that angular momentum is conserved. So it must be an increase in angular momentum. Okay, and that's it. So if you guys have any questions, let me know. I'll see you at office hours and see you for the next lecture.